So sometimes the coordinate system that we're used to using with x and y, the rectangular or Cartesian coordinate system, sometimes that's not the best system to use. And there's another system that we commonly use in two-dimension. It's called the polar coordinate system. And so in this section I'm going to introduce the polar coordinate system, show you how we plot points, and how we can convert between the rectangular system and the polar system. Alright, so just as a sort of a reminder, what are we used to? We're used to what's called the rectangular or Cartesian coordinate system, and in this system we define a point in the plane by its horizontal and vertical distances from a particular point in the plane we call the origin. Alright, so we've called this point where those axes meet, we've called this the origin, O, and it's the ordered pair 0, 0. And then any general point in the plane, right, this point, P, so this is the point X, Y, says that from the origin we've moved X units in the horizontal distance and Y units in the vertical distance from that point in the origin, and we've called that point P, X, Y. In the polar coordinate system, we take a different approach. Instead of having an origin, it's a slight change, we have a point called the pole. So let's call this point right here, let's call this the pole. And from that we build a polar axis. And it's usually drawn horizontal from that pole. So here's the polar axis. And so then we define a point in the plane with a different concept. So if here's this point, P, in the plane, instead of thinking of it as an x distance and a y distance, what we do is we think of two other components. We think of how far is it? What is its absolute distance from the pole? So I think of this distance from the pole. Let's call this distance r. And I think of its angle, its directed angle from the polar axis. So I think of this angle here, theta, where theta is measured the same way we've been measuring so far. So positively measured theta means a counterclockwise rotation, and negatively measured angle means a clockwise rotation. And we call this point P r theta. So in the polar coordinate system, we have two components, r and theta, where r is a directed distance. We'll see what that means shortly. A directed distance from the pole, and theta is the angle, the standard angle from the polar axis. Alright, so now that we have seen how we define this system of coordinates, let's now see its use. So when we have polar coordinates, we usually use a different sort of grid for it. And if you think about, when you were asked to buy graph paper in high school, it was a grid, but it was a square grid. With polar coordinates, we use a different grid. A square grid isn't as useful. So instead we use a grid that has concentric circles and radii and axes at various standard angles. And so what we do is we're thinking of this point, this center. That center is the pole now. And we tend to think of this axis right here, this horizontal axis. That's my polar axis. And so now from this, what we see is that I have radii, I have other axes that are at various angles. And so if I say, well, let's see, we've got 1, 2, 3, 4, 5, 6 axes, 6 rays going to 90 degrees, or pi over 2. That means that each axis is now broken up. This is the 15 degree axis. This is the 30 degree axis, or the pi over 6 axis. This is the 45 degree axis, or the pi over 4 axis. 60 degrees, pi over 3, 75 degrees, etc. All right, so we have the pole, we have the polar axis. I'm going to go ahead and erase my writing here for the pole. I'm going to go ahead and erase this at the polar axis. And again, then this the polar axis we can think of as 0 degrees or 0 if we're thinking about radian measure. So now let's plot some points. The point 7 pi over 6. What that means is, even though we see the 7 first, the way I tend to think of it is, I first think of the pi over 6. I think of the angle. So I'm pointing at the pi over 6. I'm pointing at the pi over in the direction of pi over 6, and I step out 7 spaces. So 1, 2, 3, 4, 5, 6. Here's the point A. That's the point A that I've measured. That is 7 pi over 6. Now the point 4, 270 degrees. All right, so 4, 270 degrees. So I've got a point at the 270 degree measure, 270 degree axis, and I'm going to step out 1, 2, 3, 4 spaces. And so then here's the point B. The point C is for negative pi over 2. All right, so negative pi over 2, well, hey, that's the same direction as 270 degrees, isn't it? Right, because negative pi over 2 is a quarter rotation clockwise. And so this is also the point C, because in that direction, 4 steps, this is also the point C. So this is something that's really important. In polar system, in the polar graphing system, there is not a unique way to define a point. In fact, any point can actually be defined by an infinite number of polar coordinates. And so that's something that's different about the polar system than the rectangular system. In the rectangular system, a point in the plane had a unique x and y that got there. And similarly, if we had an x and y, it could only go to one point in the plane. That's different than the polar system. In the polar system, any point can be defined by an infinite number of coordinate pairs. So that's something that's very interesting, I suppose, about the polar system. All right, let's go back to these points D and E. Now, in point D, we have something different here. All right, so here's point D. Here we have a negative R value. So now we have to think about this a little differently. If D is negative 6 pi over 4, we first point at the pi over 4. Let me erase my previous arrow here. So now if we point at pi over 4 is in that direction. Now if R is negative, the way I think of it is step backwards. So I'm in the direction of pi over 4, and I'm going to step backwards 1. Let me make sure I'm on the right one here. I'm going to step backwards 1, 2, 3, 4, 5, 6 points, 6 marks. So this is the point D. All right, so if R is negative, in a sense, we step backwards. Another way to think about that would be if you point in the direction, and if R is negative, you flip over the pole and walk forward. That's another way to think about it. All right, and finally the point E. E is negative 10, negative 120. Negative 120 degrees. So let me erase my previous little arrow here. All right, so negative 120 degrees. Let's see, the negative 90 and 30. So negative 120 degrees is this axis right here. There's negative 120, and then I have to go 10 steps in the opposite direction. I've got to go 10 steps backwards, and so that would put me backwards 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That would put me here. And so this point right here is E. What's another way? It's another pair of coordinates we could use to get to point E. Take a moment to think about that and write it down. So another way to get to point E would be r equals 10, theta equals 60 degrees. Right, if r equals 10 and theta equals 60 degrees, right, here's 60 degrees, and then step out 10 units. And that's not the only answer, right? We could actually say, well, 10, 60 degrees, that works. I could also have done 10, 400 degrees, right? That'll work as well, right? If I make a full rotation and another 60 degrees, I'm sorry, not 400, but 420. 10, 420 would work. Right, if I went a full rotation, a 360 degrees and 60 more, that would get me to the same, and then stepped out 10 units, that would get me to that same point. Okay, so again, there's an infinite number of ways I can define any point in the plane in the polar system. All right, so now I would like for you to practice this skill. So I've got another grid here for you, and I've got 6 more points for you to plot. So I'd like for you to pause and plot these on your own. All right, so let's see. Point A is the point 4, negative pi over 6. So if I was in the direction of negative pi over 6, that would be on this axis, and step out 1, 2, 3, 4 steps. Here's the point A. The point B, negative 6, 165 degrees. Well, 165 is 180, take away 15. So I'm on this axis. And I'm on this axis now, but I've got to step backwards 6 steps. 1, 2, 3, 4, 5, 6. There's point B. Point C, negative 9, negative pi. All right, so negative pi is a half rotation, and then negative 9. So let me erase some of these little arrows now. Negative pi, so I'm on this axis, and then 9 steps in the negative direction. There's point C. Point D, 10, 60 degrees. All right, so 60 degrees, I'm on the 60 degree axis, and I step out 10 spaces. So actually that was a point that we saw in the previous exercise. Point E, 8, negative 7 pi over 6. So negative 7 pi over 6 is that radius right there, that axis, and then step out 1, 2, 3, 4, 5, 6, 7, 8 steps. There's point E. And finally point F, negative 5, negative 210 degrees. So negative 210 would be negative 180 and 30 more. So that's actually the same radius, the same axis, however you want to think about it, and then 5 steps in the negative direction. So that would be what, 1, 2, 3, 4. It's, in a sense, it's pretty close to point A. So now, what I'd like for you to do is take these same points, and for each point, A through F, I want you to write another polar point, that would get you to that same place. So write another pair of coordinates that would get you to that same space. So now would be a good time to pause and try that on your own. All right, so another possibility for point A, and it's not the only one, but another possibility for point A would be, instead of negative pi over 6, I could use the positive 11 pi over 6, and I could still use the positive radius of 4. Another option, and again, this is not exhaustive, would be if I had negative 4 as the radius, and I used, how about the positive 5 pi over 6. And again, those are not exhaustive. Point B was negative 6, 165 degrees. How about if we had 6 and negative 15 degrees? That would work. And again, there's more than those. Point C. Point C was negative 9, negative pi. How about the point 9, 0, right? If the angle was 0 and I stepped out 9 spaces, that would get me to the same place. I could have used 9, 2 pi. That would also work. Again, there's many others that I could use. Point D, 10, 60 degrees. Well, we actually saw an example like this in the previous exercise. I could use, how about negative 10 and negative 120 degrees. I think that was the example we had, actually. Point E, 8, negative 7 pi over 6. How about 8 and 5 pi over 6? That would get me to the same place. And point F was negative 5, negative 200 degrees. Well, how about F? How about 5 and negative 30 degrees? So again, these are just a few possibilities. They're not the only ones. But just to kind of get you thinking about how we can have different coordinates getting to the same point, because we're going to see that concept in the next section. Okay, we're going to see that ideas. All right, so now these two systems, even though they're different, they obviously are related, because I can think of, if I were to just put the pole at the origin, I can kind of put the two systems together in a sense. So if I think of my traditional x's and y's, and I also put on top of that the polar axis in red, right? So here's the polar axis. And if I say, well, let the pole and the origin coincide. So now I have this point up here, and this point is an x-coordinate and a y-coordinate, but this point is also an r and a theta. All right, so now let's see. Well, there's the r. Here's the x and the y. There's the theta. Well, now, this is just right triangle trigonometry, isn't it? We know that that the cosine of theta is x over r. We know that the sine of theta is y over r. So that tells me, if I multiply through the first equation, the first set up by r, then that tells me that x is equal to r cosine theta, and y is equal to r sine theta. So if we know the r and the theta, if we know the polar point, to get to the x and the y, we just evaluate r cosine theta and r sine theta. All right, so that's good to know. And if we sort of think about that, that should look familiar based on what we've learned about vectors, right? How do we take a vector that has a magnitude and an angle and convert it to its horizontal and vertical components? Magnitude cosine theta, magnitude sine theta. Same concept, different application. Now we also know from the Pythagorean theorem that x squared plus y squared is r squared, so then r can be thought of as the square root of x squared plus y squared. The r, the magnitude, is the square root of the squares of the component, of the sum of the squares of the components. Again, same concept that we saw with vectors. What about the theta? Well, we know that the tangent of theta is y over x, and so if we wanted the theta, then theta is the inverse tangent of y over x. But here, now this one we got to be a little careful. We have to take care of the quadrant, so careful about quadrant. And so then these ideas, we can use these ideas to convert between the two systems. So here, practice, let's convert points between the two systems. We're going to write the given polar points in rectangular coordinates. So we're given r and theta, and we need x and y. Alright, so if we're given r and theta to find x and y, so then x is equal to r cosine theta. X is equal to 7. So if we're given the point 7, 120 degrees, 7 cosine of 120 degrees. So that would be 7. The cosine of 120 degrees is negative 1/2. So I don't need the cosine here anymore, sorry. The cosine of 120 degrees is negative 1/2. And so that's just negative 7 over 2. The y-coordinate is given by r sine theta. And so then the y-coordinate is 7 times the sine of 120 degrees. And the sine of 120 degrees is the square root of 3 over 2. And so then that's just 7 root 3 over 2. So then 7, 120 degrees, that polar point in rectangular coordinates is the point negative 7/2. 7 root 3 over 2. Why don't you try the next one on your own? Convert the polar point 6 negative pi over 4 to rectangular. Alright, so then x would be 6 times the cosine of negative pi over 4. Alright, the cosine of negative pi over 4, so let's see, that would be a positive root 2 over 2. So that would be 3 root 2. And y would be r sine theta, so 6 times the sine of negative pi over 4. The sine of negative pi over 4 is negative root 2 over 2. And so that would be negative 3 root 2. So in polar coordinates, so 6 negative pi over 4 in polar coordinates would be the point 3 root 2, negative 3 root 2. Now we're asked to take a given rectangular points, right? So now we have x's and y's. And we want polar coordinates. We want r and theta. And we were given a specific thing here that we want the theta to be between negative 180 degrees and 180 degrees. And we do this because otherwise there's an infinite number of answers. If we restrict the theta, then that limits the number of answers, that limits the number of points that we can use. Now, one thing that's important in this direction is that we really have to be careful about the quadrant. So if I have the point negative 5, negative 5 in rectangular coordinates, that's in quadrant 3. Okay, so we have to remember that. All right, so now then r is not too difficult. R is the square root of negative 5 square plus negative 5 square. And so then that's the square root of 50, or 5 root 2, if you simplify that radical. All right, now if I use the fact that theta is the inverse tangent of the y over the x, negative 5 over negative 5, then this would give me the inverse tangent of 1. And if we think about that, and we want degrees here, the inverse tangent of 1, that would be 45 degrees. But if we were to draw this point, if we were to draw the point 5 root 2 at 45 degrees, that's a quadrant 1 angle. And so this can't be right. So we have to adjust it a little bit. We have to put it in the correct quadrant. We need this to be in quadrant 3, so we have to use then that theta is 45 degrees minus 180 degrees. So if you remember that the tangent has a period of pi, 180 degrees, then I can either add or subtract 180 degrees as appropriate and necessary. So then we'll use the theta equals negative 135 degrees. So this point, negative 5, in polar coordinates is then, I can write 5 root 2, negative 135 degrees. Now, I could have used the 45 degrees. If I use the 45 degrees, now I'm pointing at quadrant 1, but if I need to get to quadrant 3, I step backwards. So an alternative here is I can use negative 5 root 2 and the 45 degrees. Either is correct. They both get me to the same point. All right, why don't you try this other exercise on your own? All right, so let's see, the r. The r would be then the square root of 16 plus 16 times 3, that's 48. That's the square root of 64, and that's 8. All right, so r is 8. And let's see then, theta is inverse tangent of 4 root 3 over negative 4, so that's the inverse tangent of negative root 3. All right, so remembering how the inverse tangent works, that's going to give me an angle in the negative first quadrant. And so then this is going to give me, for the tangent to be root 3, that would be a 60 degrees, so a negative 60 degrees. Now again, let's think about this point. This point is in quadrant 2, right? This rectangular point is in quadrant 2. And if I was pointing at negative 60 degrees, that would put me in quadrant 4, quadrant negative 1. So I again have two options. I either adjust the theta. So now to adjust the theta to get me into quadrant 2, I would have theta is negative 60 degrees plus 180 degrees. And so then that would be 120 degrees. So option 1, I can write this as the polar coordinate 8, 120 degrees. That would certainly be in quadrant 2. The alternative would be to keep the negative 60 degrees and use a negative r value. So negative 8, negative 60 degrees. So we've seen how to convert single points, but we can also convert entire equations. Let's see how to do that. So here we're going to take rectangular equations, x's and y's, and we're going to convert them to polar form, r's and thetas. Now, when we write polar equations, we almost always write them in the form r equals something in terms of theta, or r to a power is something in terms of theta. So we'll see what this means in a moment. All right, so here we have the equation 6x minus x squared is equal to y squared. And so I know that there's something with x squares and y squares. And so if we go back for a moment, if we go back to this slide, I know that r is equal to the square root of x squared plus y squared, or x squared plus y squared equals r squared. Let's use that fact, that x squared plus y squared equals r squared. Let's see if we can use that. So now I can move this x squared over. So then 6x is equal to x squared plus y squared. Hey, now x squared plus y squared is r squared, and the x is r cosine theta. So then I have 6r cosine theta is equal to r squared. All right, so now I can get, it's very tempting to just divide out the r, and it turns out that we can, even though we're not really supposed to. But here's why. If I rewrite this then as r squared minus 6r cosine theta is equal to 0, I can factor out the r. So then this implies that r equals 0, or r minus 6 cosine theta equals 0, and that second equation says that r equals 6 cosine theta. Now, what we usually do then is we report this as the solution, as the equation in polar form. And we throw away the r equals 0. We don't really throw it away, but we make sure, in this situation, we check, is r equals 0 a solution of the other equation? So if we look at this equation over here, this r equals 6 cosine theta, can r ever equal 0? Well, certainly r can equal 0. If theta is pi over 2, the cosine of pi over 2 is 0, 6 times 0 is 0, and so then we can throw away the r equals 0 and just keep the 6 cosine theta. All right, so let's look at a couple others. All right, so here I have 4xy equals 1. Why don't you try this one out, and the one below. Why don't you try those out and see if you can write those in polar forms. And in the end, we want r equals something just in terms of theta, or possibly an r to a power equals something in terms of theta. Now would be a good time to pause. All right, so if 4xy is equal to 1, then I can write that as 4, and instead of x, I can write r cosine theta, and then instead of y, I can write r sine theta equals 1. And so then I have r squared times 4 cosine theta sine theta equals 1. And now we can actually simplify this a little bit. If you sort of remember that 4 cosine theta sine theta, that's 2 times 2 sine theta cosine theta. And so then 2 sine theta cosine theta, hopefully you know that jogs your memory. You've heard that before. So that's r squared times 2 sine 2 theta equals 1. And so then I can write this as r squared equals 1 over 2 sine 2 theta. And it's perfectly fine to leave it like that. I wouldn't use the square root to isolate r. I would just leave it as r squared equals. And that's fine. All right, so there's that one. Let's take a look at this other one here. 5x minus 3y equals 9. All right, so let's replace the x and the y. I guess I should mention real quick that hopefully you recognize this equation. You know, this is just an equation of a line, right? This is just a line in Cartesian coordinates. Let's see what this line looks like in polar coordinates. All right, so let's replace the x and the y. 5r cosine theta minus 3r sine theta is 9. Now, notice that both of those terms have an r. Let's factor out the r. So that's r times 5 cosine theta minus 3 sine theta equals 9. And so now I can isolate the r. R equals 9 over 5 cosine theta minus 3 sine theta. And so there's the polar form of that equation of a line. Let's go in the other direction now. Let's start with polar equations and go back to rectangular form. All right, so here we have r equals 8 cosine theta, and we wish to write this in a rectangular form. All right, so these often involve a little bit of algebraic trickery. We often have to use just some techniques to get this into form as we like. And so here the issue is I can't do anything with just cosine theta. I know, however, that if there was an r here, if instead of 8 cosine theta, if it read 8r cosine theta, then r cosine theta I could replace with an x. Well, I can't just put an r there. I have to use algebra. So what I'm going to do is I'm going to multiply. Let's multiply this side of the equation by r. Well, if I multiply one side of the equation by r, I have to multiply the other side of the equation by r, right? That's what we have to do. So then this becomes r squared is equal to 8r cosine theta. R squared is x squared plus y squared. 8r cosine theta is 8x. And hopefully you recognize this back, if you're taking pre-calculus, you should certainly recognize this. If you haven't taken pre-calc or you're not taking it yet, you may not. But this is the equation of a circle. And in pre-calculus, we learn how to write that equation of a circle in a standard form. And so what that means then is that original equation, r equals 8 cosine theta, that must also be the equation of a circle. What if we had r equals 4 over 2 cosine theta plus 6 sine theta? Why don't you pause and try that one out on your own? All right, so this one, it's tempting. It's tempting to to use what we used in the last example, to maybe somehow multiply this denominator by r, but then we'd have to multiply this numerator by r, and then I've got a 4r, and I don't know what to do with 4r. So that's tempting, but not the best approach in this case. So what I'm going to do instead is I'm going to get rid of the fraction. And so I'm going to multiply both sides of the equation by the common denominator. 2 cosine theta plus 6 sine theta. Right? So I'm going to multiply. So I'm multiplying the right-hand side by that same quantity. And so notice then that takes that quantity and multiplies it by r. Distributive property. Then I'd have 2r cosine theta plus 6r sine theta equals 4. R cosine theta, that's x. 2x. R sine theta, that's y. Plus 6y equals 4. An equation of a line. Now these last two examples on this page are special cases. If you remember back in algebra, we learned some special cases in the rectangular form. We learned that if we just had x equals a number, we learned that that was a vertical line. And we learned that if y equals just a number, that was a horizontal line. And so what happens if we just have r equals a number or theta equals a number in the polar system. All right, so r equals 9. The radius, the directed distance, is always 9. Hey, that's going to be a circle. It's going to be a circle of radius 9. Let's show that in Cartesian coordinates, in rectangular coordinates. So if r equals 9, and the trick we use here that we can't use most of the other time is, I'm going to square both sides. I'm going to square both sides. Now that might introduce extra roots, but that's okay. It works here. So then r squared is 81, and r squared is x squared plus y squared. X squared plus y squared equals 81. That's the equation of a circle centered at the origin with, wait for it, radius 9. The radius, if we go back to the original equation, the radius was 9. And if we look at this equation, x squared plus y squared equals 81, what's the radius? 9. Right, circle centered at the origin, radius 9. A circle centered at the pole, radius 9. It's the same concept. If the theta, if the angle is pi over 6, if the angle is always pi over 6, if the angle doesn't change, then r can be any point on that line. It's a line with angle pi over 6. All right, so the trick here is, if theta is pi over 6, take the tangent of both sides. If theta is pi over 6, then tangent theta is tangent of pi over 6. So then tangent theta is equal, now the tangent of pi over 6, that's 1 over the square root of 3. All right, now if you remember back, if we go back for a moment to that, go back to our converting points here, notice that tangent theta is y over x, right? So if we use this fact, that the tangent of theta is y over x, then y over x is equal to 1 over root 3. And so then I can write that as the equation y equals 1 over root 3 times x. That's a line through the origin with slope 1 over root 3. All right, so if we have just theta equals an angle, we get the line of the form y equals the tangent of that theta as the slope times x. So those are a couple of special forms that we should be aware of. All right, so that completes this section on this introduction to polar coordinates and how we convert between the two systems. In the next section, what we do is we learn how to sketch equations that are in polar form. And I'm going to show you a couple different approaches to that. And we get some interesting graphs, things that we can't easily do in rectangular coordinates that are relatively easy in polar coordinates. All right, so have a good day.